In this module, we'll strip blockchain down to its essentials, then rebuild it for regulated, real-world environments. You'll see how ledgers, consensus, and smart contracts move beyond cryptocurrency and become core building blocks for compliance, audit, and institutional trust. When most people hear blockchain, they think speculation, price volatility, anonymous users, content that can't be censored, and a culture of code is law where software rules everything. In enterprise and government work, that mindset is almost inverted. We use the same underlying technology to get immutable audit trails, so investigations and audits have strong evidence. We link actions to real-world identities, so accountability is explicit. We care about deterministic settlement finality, not trading. And instead of replacing law, we design systems where legal frameworks and code reinforce each other. Now think of a blockchain as a digital chain of custody. Each transaction is an authenticated state change. Who did what, to which asset, under which rules. Those transactions are batched into blocks, which give you ordering and a trusted timestamp, like sealing a page in a logbook. Each block then commits to the previous one via a hash link. That hash makes any change to history immediately obvious, because every later hash breaks. Enterprises and governments rely on this property to prove integrity over long time frames without having to trust a single log owner. Merkle trees extend that idea by giving us a compact, verifiable fingerprint of a large dataset. Instead of storing or transmitting every record, we store a single hash, the Merkle root. When someone asks, was this transaction really part of that dataset, we don't resend everything. We provide a short Merkle proof, just the hashes along the path. Recomputing those hashes recreates the same root, or it fails, so tampering is obvious. For regulated environments, this is powerful. We minimize data exposure, yet still deliver strong integrity guarantees and auditable evidence for compliance. In regulated environments, blockchain isn't just about shared data. It's about binding actions to real-world identities and making them stick. Verified identity, often through KYC and PKI, tells us who is allowed to act. Digital signatures then cryptographically link that person or organization to each transaction. Together, this gives us non-repudiation. They can't later deny what they did, and admissibility, because the ledger can serve as forensic-grade evidence in audits and legal disputes. Under the hood, there are two main ways ledgers represent state: UTXO and account-based. UTXO treats value as discrete outputs that are either fully spent or unspent. Each transaction consumes specific outputs and creates new ones, giving you a precise graph of where every unit came from. That's powerful for provenance, audits, and fine-grained controls. Account-based models track balances per identity. You simply debit one account and credit another. It's easier to reason about, maps cleanly to enterprise accounts and workflows, and tends to simplify smart contract logic. When we talk about consensus in regulated systems, we're really talking about a different primary goal. Public, permissionless chains optimized for censorship resistance and always-on availability. No one should be able to stop a valid transaction. Enterprises and governments care more about finality and accountability. Decisions must be unambiguous, attributable to specific parties, and defensible to regulators. So consensus design becomes a governance question. Who proposes blocks? Who validates them? And when is a decision legally final? Proof of work was revolutionary for open public cryptocurrencies, but it clashes with enterprise and government requirements. It burns huge amounts of energy, which raises cost, sustainability, and ESG concerns. Its probabilistic finality means you must wait for multiple blocks before a transaction is truly safe, which is too slow for many business processes. And because validators are anonymous, there's no clear accountability, which is unacceptable in regulated environments. In enterprise and government settings, the de facto standard is Byzantine fault-tolerant consensus with deterministic finality. Protocols like PBFT, Raft variants, or Hot Stuff assume a fixed known set of validators, typically a consortium of regulated institutions. That lets you trade anonymous openness for strong guarantees. Deterministic finality means once a block is committed, it's final in seconds, not probably final after many confirmations. Because validators are identified organizations, misbehavior is attributable, auditable, and legally enforceable, exactly what regulators and internal risk teams expect from mission-critical systems. Choosing a consensus mechanism for an enterprise or government network means navigating a four-way trade-off: throughput and finality speed drive, whether the system can actually meet business SLAs. Energy efficiency matters for cost, sustainability reporting, and often public perception. Decentralization determines how much you can really trust the network not to be captured or censored by a few players. Proof of work pushes decentralization and security, but pays in energy and latency. Proof of stake improves efficiency and speed. Enterprise BFT goes further, optimizing for performance and fast finality, while accepting tighter, governed decentralization. You can also think about blockchain networks along a spectrum of access and control. On one end, public permissionless networks maximize openness, but you have very little control over who participates or where data flows. That's difficult for GDPR, data residency, or sanctions compliance. On the other end, fully private networks give maximum control, but you lose the benefits of shared, multi-party governance. For most enterprise and government scenarios, the sweet spot is consortium, permission networks. You still share a common ledger, but strict identity, onboarding, and role-based access control let you align with regulatory and policy requirements. Public blockchains are powerful, but for regulated organizations, they're usually a poor fit as primary trust infrastructure. Immutability clashes with legal deletion and correction requirements. Global, permissionless nodes make data residency practically unenforceable. And when validators are anonymous, there's no clear party you can hold accountable or sue. In this context, public chains are best limited to anchoring hashes, timestamps, or other non-sensitive proofs. Consortium networks are therefore the dominant pattern for regulated blockchain deployments. Instead of one central operator, a group of known, vetted institutions jointly run the ledger and share control. Every node operator is identified and governed under a legal framework, so blockchain rules and real-world law reinforce each other. This model fits use cases like interbank settlement, supply chains, and government records, where accountability, compliance, and predictable governance are mandatory. When you match architecture to a regulatory use case, always start from the legal requirement, not the technology you prefer. If the law or policy demands public verifiability or citizen challenge rights, you usually need a hybrid model with some public anchoring, so external parties can independently verify history. If regulators care most about high privacy and throughput between known institutions, a consortium BFT network is often the right fit. If the requirement is purely an internal audit trail, a tightly controlled private ledger may be sufficient and simpler to govern. To pull this together, think of blockchain-based trust as a stack you intentionally design. At the base, you anchor identity so participants are known. On top of that, you manage data so it's private, pruned, and provable. Then you choose consensus that's fast and final. Finally, you get an immutable, auditable record. Done well, this stack upgrades integrity, strengthens accountability, and quietly automates large parts of compliance.